Okay, today we are going to talk about Huffman coding. Huffman coding at the end has a tree structure, and I will show it later. Main goals and main reasons why we use Huffman coding is that we encode symbols that have some probabilities, and the underlying tree structure can give a very good possibility to do that. Then Huffman coding is an optimal scheme. Results are very close to the entropy. Huffman tree is very easy to build and it has intuitive structure, and Huffman tree concept can be modified for upgrades. I will show 3 of them. The idea of Huffman coding is to give lower probability symbols longer code, and for bigger probability symbols shorter one. To do that, we're going to consequently merge 2 nodes with smallest probabilities on each step, and thus we will produce nodes which contain probabilities of some symbols, and we will move according to these probabilities through the tree and the acquire codes. I will build a tree now and you will understand what I mean very good. I made first 3 steps of the algorithm. So first we merged I and T and has given them their cumulative probability. If we continue, we can merge R because it has the lowest probability and the merged node. Thus we acquire newly merged node. Now we're in a situation we have to merge R and this merged node, and the tree will become a little messy because they have the lowest probabilities. It will be 4. Now we merge these ones and at the end merge them together to the 1. 1 is 100% probability. 3 is a little messy. I will rewrite it in a couple of seconds and you will see and I will describe the missing parts. Okay, I've rewritten the tree. Once again, to make it absolutely clear, on each iteration of our algorithm we are looking for the 2 nodes where the probabilities are the smallest. We merge them and continue with new formed node and other nodes we didn't use. Thus we acquire tree-like structure. It's a binary tree where we converge to probability of 1, so probability of 100. Probability of all symbols together when we sum it up will be 1, so 100. And this is the Huffman tree. How do we actually encode things using Huffman tree? It's super easy. To encode something with a Huffman tree, we move to symbol we are going to encode, and on each move to the right we add 1, and each move to the left on the tree we add 0. Let's try to encode, let's say, D, E, R using our Huffman tree. So you can think of it, how to do that. D will be encoded by moving in this direction and in this direction and once in this direction. Thus it will be 0, 1, 0. How to encode E? It will be 0, 1, 1. And how to encode R? It will be 1 and 0. Actually, it's not the only way to build Huffman tree using these symbols and these probabilities. They can vary a little depending on which nodes you merge, because sometimes merging nodes can have same probability. For example, D and E could have gotten the same probability if we merge them with some other node, and thus you could have merged with E or with D, for example. Today we are also going to talk about canonical code. I've given the outline of the algorithm as always, and you can a little focus on it, and then I'll give an example. Actually, the idea here is no more and no less than to assign new codes uniquely decodable by code word length. Okay, let's say that after Huffman coding we've got these codes for these symbols, to concatenation of the symbols, that's no matter now. And we've got these codes as we moved through the tree and we produced these codes. We assume that. And now we calculate the lengths of the code. Now we formulate new codes, canonical ones. And it's done extremely simple. We start from 0, 0. For each following code word, add 1 to the preceding code word in binary. Yes, these are canonical codes. Once again, we started from 0, 0, added a preceding one to like here, and padded with 0 here. What we did, we took 2 zeros, put them here, added 1, and padded with 0 from the right, because our code has to be a length of 3. Here, we took this code, added 1 to the place of 0. Here we took this code, added 1 in binary, and if we add 1 in binary to this number, we will produce this number in binary. Here same, plus we added 0 to the end because of the length 4. And in similar fashion we continue up to the very end. I think it's clear.